Hello everyone. So today we'll start with the first module of analysis of determinate structures, and the first module includes slope deflection method. So in this method, basically we'll be finding the slope and deflections at every joints. So as we have already studied that indeterminate structures are the structures wherein the equilibrium equations will be only three, and what we have to find will be +1 or +2. So the number of unknown equations will be greater than 3, but we have only 3 equilibrium equations. So there will be extra unknowns to be found out. So those unknowns will be found out using the other methods. So the first method of this analysis of indeterminate structures is slope deflection method. So basically it is itself in the name that there is a slope and deflection. So we'll be finding the slope and deflection at every joint of the given member. So there are assumptions made in this. So the first assumption includes all joints are rigid. Angle between any two members in a joint does not change even after the deformation due to loading. Okay, you can see here the first figure, A, B, and AC. There are two members with an angle theta. Okay, so this is before deformation. So if you try to deform this or tilt this, so initially it is AC. So if you try to tilt this, so AC changes from AC to AC dash. At the same time, the angle is maintained and AB changes from its initial position to AB dash. So the meaning of this is this theta is equal to this theta. So every joints are rigid. So the meaning of this is before deformation, the theta remains even same after deformation also. So this theta angle is maintained. That is the first assumption. Due to deformation, the angle theta is maintained throughout the lifespan of the beam. Okay, the next assumption is distortion due to axial deformation are neglected. I can see this. Initially, this is a frame. So it is a frame which is fixed at A and D, and it is pin jointed at B and C. So AB, BC, and CD. So this is a frame before deformation. The bold lines are before deformation. So if you apply a force like this here, the sway force, okay, you apply any force at B, obviously because these are fixed, they will not move. So only joints which distort is B and C. So you can see here B changes from B to B dash, C changes from C to D, C dash, and the delta between them, that is the horizontal movement between them, is same. Okay, so now B dash is equal to C dash, and this is delta. Now this is the horizontal displacement, or it's also called as a horizontal distortion. Now this distortion is neglected. So what we are going to assume that even if there is any sway force acting on the beam, it is assumed, because it is very negligible, so it is assumed to be zero. Okay, so distortion is neglected because of this sway force, and more specifically in the framed structures. This is the second assumption. Third assumption is shear deformations are neglected. Okay, now the shear deformations means distortion of rigid joint structures due to axial forces and shear are really small compared to distortion due to flexion. Okay, so the meaning of this is if you apply force anywhere between AB, BC, and CD, if you apply load here, say in between AB or in between BC or in between CD, the most important displacement or flexure which will take place here at this portion is here. So when you apply a force, for example, if you apply force at AB here, obviously it will bend like this. Okay, it will sag like this. Or to be more, if things can change. Okay, now if you see here in BC, if I apply a load here, exactly at the center in BC, obviously this beam will be bend, it will bend down like this. So when it bends down like this, so the most dominant change happening here is the flexure, that is bending. So shear is very negligible. Okay, between AB and BC, the shear force is very negligible, or the shear moment is very negligible. So the dominant parameter which occurs in B and C is the flexure. So that is what is being told here. The third assumption is shear deformations are neglected. So quickly, just let us take a look of the assumptions. So first assumption is all joints are rigid. That is, the angle between any two members will be same even before deformation and after deformation. And the second assumption is distortion. That is, if any sway force is acting on the frame, that will be neglected because it's a sway force and it is a horizontal force. And this displacement, horizontal displacement, is very negligible, very small. That's why we're going to neglect it. This first. Second thing. Third thing is shear deformations also neglected. Again, shear deformations, because when you apply a load in any part of this member, the dominant factor here is the flexure takes place. So we are more interested in the flexure of the beams, and hence the shear parameters, of course, shear exists is because it is very minute, very small, and hence it is neglected. So these are the three assumptions we are going to make throughout this module. Okay, after this, then there is sign conventions. Okay, so the first sign convention here is like what we have studied in SOM, that is bending moment and shear force sign conventions. The same sign conventions will be applicable here also. So here the first one is moments. So what we are going to assume here is, you can see here, this is a framed structure. So in this frame structure, A at end A it is fixed, and D it is fixed. So because it is the fixed support here, all the displacement and horizontal displacement, vertical displacement, and rotation here is 0. Okay, now if you check this here at B and C, now the first assumption here is, no matter whether it is a horizontal beam BC or a vertical column AB, here we are going to assume the clockwise movements. Okay, the clockwise movements are always considered positive. You can see here, it is going clockwise, so it is positive. And this is in span AB. Because it is in span AB, I'm going to show this moment here as clockwise positive. Now the same moment, now see here, end joint B has two members, that is BA. We are going to read it like this only because we are going to specify joint B here. So joint B has BA at one end and BC at other end. So when you check this out, that is BA, that is, we are more specifically talking about the column. So in this column, so all the clockwise movements are positive. So this is relatable to columns as well as beams. So in this, clockwise movements are positive. The same joint B, now if I try to relate this to this beam now. So in this beam, now if you check this out, this is going anti-clockwise. This moment is now anti-clockwise. So the anti-clockwise moments are taken as negative. So when you try to write this, so M means moment. First, B means joint B. It starts at B, ends at A. That's why we write it as MBA and not the other way around. That is MAB. MAB will be acting at joint A. So the first letter after M, the first letter indicates the joint. Second letter indicates where the joint ends. So this will relate to the complete member. So moment at B from B to A. Okay, so when you check this out a column, so it is now shown it clockwise. So clockwise I've written plus. So it is plus 20 kilonewton meter. Now because we're talking this about the movement, so movement, unit of movement is kilonewton meter. Likewise, now MBC. So movement at B to C. So movement will start from B end to C. That's why we've written it as movement starts at B, ends at C. So the first letter is B and then followed by C. So now if I check this arrow, now this arrow is anti-clockwise. Okay, moment is anti-clockwise. So because it is anti-clockwise, according to the sign conventions, it would be minus 20 kilonewton meter. So this is the first assumption we're going to make. Whether it is a column or a beam, all the clockwise movements are positive and anti-clockwise movements are negative. Okay. Then the second sign convention is the rotations. So rotations are nothing but the slopes, okay, theta, the value of theta. Now you can see here, it is a continuous beam, okay, AB, BC, okay, these are all continuous beam. Now see here, indeterminate structures are the structures wherein there are more than two spans, okay. So if what we have studied earlier was there would be only one span. So one span means there would be only, those are all determinate structures where there would be unknowns would be only three, and those unknowns used to find by using three equilibrium equations. Now here unknowns are 1, 2, 3 and 4, only the theta values. You can see here all the theta values of 4, but you have equations of equilibrium as 3 only. So again there would be an additional unknown. So such problems can be solved and they are treated as indeterminate structures. Okay, so again in this you can see here the rotations. Okay, so all the clockwise rotations of tangents to elastic curve is positive, and anti-clockwise rotation is negative rotation. Okay, all right, so you can see here first one in this case, it is AB and BC span. So end A is hinge support, B is roller, and C is also roller. So now what I've shown here is the elastic deformation of the beam. Okay, now you can see here how I've drawn this is when the load is applied here, obviously the beam will bend down like this. Okay, so that's how this is the deformed shape of the beam. Similarly, from B to C, now because it is continuous, whatever this bend shape, it will stop here and it will go the other way here. Okay, so here it is sagged, here it is hogged. That is the nature of continuous beam. Okay, that is the nature of this continuous beam. So now this, it goes like this and ends here. Okay, now this diagram is nothing but the elastic shape of the beam. Okay, now what they've told us, the clockwise rotation to the tangents. Okay, now at every joints, I'm going to draw a tangent. Okay, now see here, this is joint A, right? Joint A, it should start at joint A, and we draw a tangent. It should touch and cut this joint. See here, it should start from this joint and then it should pass over the elastic curve. So we draw it like this. So joint A, draw a tangent. Okay, similarly joint B, now see only the left side of B. So joint B, just draw a tangent like this, only at this portion as of now. Okay, it should start from B, then it should cut the elastic curve. Similarly, again, next check the span BC. So in span BC, it should start at B, cut this section here, cut this portion, and then it should pass over the elastic curve at B in span BC. Similarly, at C, it should start at C, then it should cut and trace over elastic curve, this portion at C. Okay, now after this, this is the original shape of the beam and this is deformed shape of the beam. So now you should decide how the rotation has taken place from the original shape to the deformed shape. You can see here, just draw a line here, just show an arrow. Now then check, this is the original shape, deformed shape. So how it is moving? How is the deformation happened here at A? Okay, so the deformation happened here at A is clockwise. Okay, so it is theta 1. Similarly, check out at theta 2. So this is initial shape of the beam, original shape. Then this is the deformed shape. So from initial to deformed, now it is just draw this arrow. Okay, then now this is going anti-clockwise. Next, similarly, then this is the original shape and this is the deformed shape. So original shape, with respect to original shape, check the deformed shape. So again, this is going anti-clockwise. Okay, theta 3. And the last one, original shape and deformed shape, draw a arrow. So this is also clockwise. All right, so now sum up all the clockwise and anti-clockwise rotations. So the clockwise rotation here is theta A. So theta 1 is going clockwise, then theta 4 is also going clockwise. So theta 1 and theta 4 are positive rotations. Okay, similarly, then check out anti-clockwise. So theta 2 is also going anti-clockwise, theta 3 is also going anti-clockwise. So these rotations are taken as negative. That's how we sum up this rotations. Okay, so all the positive rotations are written with respect to the clockwise movement. So if there is a clockwise rotation, then it is positive. Anti-clockwise rotation, negative. Okay. Next is the settlement. Okay, now this is very important to understand. All right. So this rotation is nothing but this settlement is nothing but we use the term delta. Now, delta is taken as positive. Delta is taken as positive if the right hand support, is below left hand support. Okay, this is very crucial throughout. Okay, just pay attention and listen to this very carefully. Now see here, this is also fixed beam at A, and this is fixed at C. At B, there is a roller support, right? Okay. Sometimes due to the loading, there are chances of the support sinking. Settlement means sinking of the support. Due to the load, okay, even the support sometimes sinks. That means it goes below the straight line. Okay, in this figure, you can see here, AB is a span of length L1 and BC is span of length L2, right? Now, because of the load, sometimes the support sinks. Sinks means you can see here. Now this B is changing its place. Originally it's like this, A, B, C. It's in the straight line. Now because it is sinking or it is settling or the settlement is happening. So what happens? From B, it is changing its position to B dash. You can see here. Now the actual beam looks like this. A to B and B to C. Okay, now this is the deformed shape of the beam. Now, how much is the deformation happening here? That is nothing but delta. So this is nothing but settlement. Now, under such circumstances, we have to take the sign conventions. Now, how to consider this is, now, if the settlement, you can see here, this is AB. Okay, just consider only AB span here. Now, if in AB span, if the support is below, okay, now suppose this is A support and this is B support. Now support is sinking. If the right hand support, consider only AB span. So A is on the top, B is at the bottom. Consider only this portion, deformed portion, and only AB span. So it is, we are only talking about A and B dash. Okay. So in this A and B dash, if you see this, A is in the original position, but B is sinking. Okay. So that is nothing but, you can see here more specifically, it is like this. When the right side support sinks, okay, we'll consider only in this module, what we'll be doing is every member will be splitting it and choosing the sign conventions and marking all the sign conventions here. Okay, now see here, right side. So it only span, there is only one span with the right support. So this is like, if you see the span, this is left support, this is right support. Okay, so if the right support sinks, so initial position is this, but it is going down, it is sinking. So if it is sinking like this, if the right support is sinking, then it is positive. Okay, similarly, okay, now you consider to the BC support. So you can see here in BC support, okay, B is already sinking now. So we'll be more specifically talking about B dash and C. Okay, in this portion, only this portion, B dash and C. We are more interested in this portion now. Okay. Now again, when you see this, so according to this, this is left support, and this is right support. Okay, left and right support will be same throughout. Okay, so this is left support and this is right support. Now this delta, this support sinking, will be taken as negative if the left support is below the right support. I can see here, only consider only this span B dash C. B is sinking, that means left support is sinking, right support is above. Left is below, right is above. You can see here specifically. So again, this is left support, right support. Here also left support, right support. In the first case, left support is straight, right support sinking. So right support is sinking, then it is positive, and vice versa. So the left support is, if left support is sinking and right support is straight, then it is negative. Okay. Okay. So let me just simplify this finally. So how to remember this is, whenever you consider left support and right support, if the right support sinks, then it is positive. When the left support sinks, it is negative. Okay, that means the settlement, this plus delta means that is the settlement. Settlement will be taken as plus delta if right support is sinking, and it is taken minus delta if the left support is sinking. Okay. After this, we have this derivation of slope deflection equation. Actually, again, the derivation is not that important for y'all. So what you'll have to understand here is the final equations we'll be considering here. Okay. Okay. Now these are called as slope deflection equations. Okay. You can see here, these are important. MAB is equal to, that is here, moment in AB, moment in span A, which starts at A, ends at B, is equal to MFAB. Now this is nothing but M means moment, again it's called as moment, but it is now F, the term F indicates fixed end moments. Okay, as and when we solve problems, I'll tell you what exactly is the fixed end moments. Okay, so MAB is equal to MFAB plus 2EI by L into 2 times theta A plus theta B minus 3 delta L squared. Okay, now you can see here. So MFAB is nothing but moment, that is fixed end moments. Fixed end moments in span AB plus 2 EI, again EI values will be given in the problem. So EI is nothing but flexural rigidity divided by L, and theta A, 2 times theta A. Now theta A is nothing but rotation in end A plus theta B, far end B, minus 3 times, again delta is nothing but the settlement, or it's also called as sinking of the support, divided by L square. Now these are important. So these are the slope deflection. The method slope deflection, in slope deflection method, we'll be using the slope deflection equations only, okay, to further solve the problem. Okay, similarly, now this is for AB, starts at A, ends at B. Similarly, MBA, if you're finding MBA, okay, MAB is not same as MBA, because MAB start point is A, end point is B. Similarly, MBA means start point is A, end point is, start point is B, end is A. So moment in B and A. Okay, again it is same thing. MBA is equal to first MFBA. So it goes along with this only, that is fixed end moments. So here it was MFAB. So here it is MFBA, because we are talking about B to A. So it is MFBA plus, again this is same, 2 EI by delta, 2 EI by L. So here also same, 2 EI by L, 2 EI by L. Okay, now because the start point here is B, so whichever is the start point, at that point you have to multiply 2. Okay, so again the sequence would be same, theta A, theta B, 3 delta by L square. But the only thing that changes here is, whichever is the first term here, that term would have 2 in it. You have to multiply 2 times theta B minus 3 delta L. So if you try to compare this here, both the equations. MAB is equal to first point MFAB. Here MBA, MFBA. Okay, first point B, first point A. Similarly, next 2EI by L, 2EI by L. That is same throughout. Okay, first, because the first point is A here, you have to sequence, you have to write the same AB only. Sequence AB only. Here also AB only. But because it's the first point, A means you have to multiply with 2 because the first point. So 2 times theta A plus 1 time theta B minus 3 delta by L square. Okay. Similarly, MBA here again, first point is B here. So because the first point is B here, you have to write theta A as it is. Because the first point is B, you have to multiply 2 times of theta B minus 3 delta by L square. Okay, these are the slope deflection equations. Okay, so as and when we solve the problems, you'll again things become more clear. So where can you use this? So the applications for this is mainly it is used for continuous beams, frames without sideway, and frames with sideway. Okay, so all the slope deflection equation on all the methods what we'll be using here will be all be used for indeterminate structures. So again, indeterminate structures are the structures where the unknown parameters are greater than 3. Okay, so that's all for today. We'll continue in the next class. Thank you.